With that, I'll hand over to Ray Kinsella. Ray Kinsella has been working on Linux and various other open source technologies for about 20 years. He is recently active in open source communities such as VPP and DPDK, but is a constant lurker in many others. He is interested in software Dataplane and optimization, virtualization, operating system design and implementation, communications and networking.
I should say thank you to Sujata for inviting me today. And I really mean thank you, because I just flew in from Phoenix, and to be honest, any excuse to get out of the sun.
But before that, before coming to Phoenix, where did you come from?
Oh, I'm based in Ireland, and I was in, my boss is based in Phoenix. And my boss was complaining towards the end of last year, all of his team is remote. And he said, all you guys are remote, you know, there's nobody actually physically in the office, I'm lonely. And I said, yeah, I'll come out and visit you. And I said, the only problem is I can only really come out during the school holidays because my kids are off in July and August. And he said, no, come out to Phoenix, it's beautiful in July and August. Yeah. So my wife just flew out today. She just flew home with my two kids, and my son's 5. He's starting school in about 2 weeks, so she's got to go home and get the books and the uniform. So I dropped her at the airport before getting on a flight myself, and she said, I'm never coming back. No. So I work on Dataplane problems, and that's my comfort zone. I work on the optimization of the data plane on microprocessors, and I've been working on DPDK for 8 or 9 years, always as a lurker. You know, I'm always somewhere in the background and messing with some code. Yeah, over the last year, 18 months, I've been playing a lot with VPP. So today I'm going to talk about both DPDK and VPP and containers, because the scaling story is becoming important. For DPDK, when it was designed to consume all the cores it was given. It makes assumptions about memory utilization. It makes assumptions it's going to have physically contiguous memory. It makes assumptions it's going to have large blocks of memory. It makes assumptions it's not sharing cores with other applications. Whereas, you know, we look at where the future is going to microservices model, we'll have to move to a much more, let's say, friendlier model where we share those resources with our applications. And that's what I'm going to talk a little bit about today, how we make that happen. And I'm going to talk about it in the context of both DPDK and VPP. Now, last time I tried to talk about DPDK and VPP in the same presentation. I learned the hard way that saying DPDK and FDIO VPP in one sentence at the same time is exceptionally hard. So if something doesn't make sense at any time, if I'm referring to DPDK and it's not clear if I'm also referring to VPP, you know, stop me, because I do better when it's an interactive session. So please stop me, ask questions. It'll make for a much more interesting session. So what I'm going to talk about today, I'm going to talk about why containers and the challenges of containers. I'm going to introduce FDIO VPP. I've already, from talking to people outside in the lobby, I know there's a lot of people who are already familiar with FDIO and VPP, but there are also some of you who aren't. So I'm going to talk, I have 2 or 3 slides introducing FDIO VPP. I'm then going to talk about the challenges of scaling the container data plane for both virtual network functions and then also for virtual switching, and that is for both VNF and NFVI use cases. And I'm going to talk about a couple of different approaches for virtual switching. And then I'm going to do a short presentation to show, hey, containers and VPP is really easy. And hopefully that won't explode as any demonstration. I don't know if anybody has done live presentations in the past. I've done buckets of them over the years. And one thing you can be guaranteed without fail is that it'll work a million times until you're standing up there presenting it, and then it'll all fall apart, as inevitably happens. But we'll give it a try anyway. So, why containers and the challenges of containers? So I borrowed this slide from AT&T because I really liked it. And what it shows is AT&T presented this in OpenStack in Boston. And it shows the evolution of their network over time. It shows their enterprise IT workloads today are containerized, and many of them are microservices. And then they have a small number of VMs servicing enterprise workloads. And then what we can see is from today, 2017, through 2018, 2019, we can see that the number of VMs really drastically reduces and the number of containers grows. And we can also see that the virtual network functions, those packet processing applications that they have in their network today are based on virtual machines. But they expect that over time, the number of virtual machines, again, to shrink and the number of containers are growing. So for many, many expect that 2018 is going to be an inflection point for containers and virtualization. So where we've seen in the telecom network. So to date, we've seen many discrete appliances get turned into virtual machines. What we will see in 2018 is many of those virtual machines turning into containers. Now, where it goes beyond that, it may just stop there. We may just see packaging change. We may see applications that were previously packaged as virtual machines get packaged as containers. But the actual architecture of the application not change dramatically. So the actual decomposition of those applications into microservices is a separate step. So this step between 2017 to 2018 to 2019 may just be a change in packaging for an existing application. Something that was previously wrapped up in a virtual machine gets wrapped up in a container. But the application's architecture doesn't change dramatically. It then is an additional step to take that application and to decompose it into a series of microservices and deploy those in the containers. And I'll talk about that a little bit more in depth in a couple of slides later. But it's important to understand that there's two trends going on here. There is both a trend away from virtual machines to containers, but then there's also a second trend, which is a decomposition of VNFs into microservices. Does it make sense to everybody? I see nodding heads. Now, the other reason, I had a slide here and they made me take it out. And I was at FOSDEM in Belgium. Anybody who's around open source as long as I am will know FOSDEM. Anybody been to FOSDEM? I'm in the west coast of the US, so I know it's a long way away from here. No, AB guys. So FOSDEM, if you ever get a chance, it's a free conference in Belgium. And it's incredible fun. It's great fun. You don't have to pay anything to go to the conference. You just register. It's all sponsored. All the things are sponsored. But the actual conference is run very much by a team of volunteers. So you end up people bring their kids to the conference. So you'll have people bringing their teenagers who are just getting interested in technologies. You also have people who can't find babysitter also bringing their kids to the conference. But the amazing fun thing about it as well is that there's bars at the conference, so you have people walk into the lecture halls with a beer in their hand as well. So it's a very informal, fun conference, and it's been on the go for a long time, and it's great fun. I've been to it. I've been lucky enough to go. So it's not a big trip for me. I've been lucky to go to it several times. It's been enormous fun. I tried to get into the containers room. I tried to get into the containers, Kubernetes, and microservices room. I had to wait outside the door for an hour, and eventually, when I got in, there was people sitting two to a chair. People sitting down the front, people sitting everywhere, guys hanging out of the ceiling. Because that's how hot the technology is at the moment, and that's how interested people are in microservices and containers. And I think that also is a factor at play here, is that, many people, some users are looking at those applications that were previously, that came from discrete boxes, are maybe getting deployed as VNFs, and looking at the benefits of microservices, both the robustness and the scalability, and seeing, okay, how can I take my application, how can I take my VNF and realize those same kind of benefits? Okay. So I think I made the point already pretty well that just because containers doesn't equal microservices, so you can change the packaging to be from a virtual machine to container packaging, but it doesn't necessarily mean that it's a microservices. The decomposition into microservices is another step, and it's another trend entirely. But when people think about containers, they think about microservice-like behaviors. Now, I like this from Peter Willis, where he said operators, that's network operators, will have to start, Peter Willis, sorry, is the chief researcher for converged networking at BT, British Telecom in the UK. So the operators will have to start treating their network functions less like pets and more like cattle. So the analogy is that pets are like the VMs. They're relative, I have a few of them and I know where they are most of the time. To where those VMs, those pets become more like cattle in that I have very large numbers of them and their life cycle is very short. I spin them up and I tear them out and I don't even think about them. So when people think about microservice-like behaviors, what do they expect? Well, they expect decomposition. They expect something that's relatively modular. They expect it to be relatively stateless, or to indeed have minimal state. The more state you have, the less lightweight you are. They expect it is to support a rapid life cycle. So that is the ability to set it up, and tear it down in microseconds. They expect it to be relatively lightweight in terms of its CPU utilization, its memory utilization, and its I/O. And then lastly, because of all of these previous characteristics, they expect it to be very scalable to the many thousands on any given node. So keep this in, as we're going through the rest of the presentation, keep this in your mind, keep this in mind. Because this is our challenge, is to take DPDK and to take VPP, and these are really applications that were designed to consume all of a core, is consigned to use large amounts of memory and consigned to use large amounts of I/O, and to make assumptions that it's exclusively running on that core, it has exclusive use of the memory and has exclusive use of the I/O, to something that's much more able to share. So now I'm going to jump for a moment and I'm going to introduce FDIO and VPP. So by a show of hands, because I haven't had any questions yet, I'm going to have to make it a little bit interactive. By a show of hands, how many people are already familiar with FDIO and VPP? Okay, that's a fair few. Okay. So for a long time in the DPDK community, DPDK was a I/O layer. It was a hardware abstraction layer. It was a way to talk to your network card, to your crypto devices, and also a very highly optimized packet processing environment. We gave you APIs to send and receive packets. We gave you APIs to allocate memory. We gave you APIs to you make most efficient use of the memory channels, to allocate huge pages for your memory, to reduce TLB misses. We had a whole slew of optimizations we built into DPDK. And the idea was that if you built your application on top of DPDK, you would get the benefits of all these optimizations. But what we didn't have was we didn't have an L2 and L3 stack. We had L2 or L3 sample code, but we didn't have a L2 or L3 sample implementation. So Cisco approached us in 2000, at the tail end of 2015, and said, we've had this stack in development internally in Cisco since 2002. It's roughly based on DPDK, give or take today. And we're interested in it, contributing it to the open source community. And in many ways, it was at that time what we felt we were missing in DPDK, which was a high performance L2, L3 implementation. So FDI, and we built a community around it. We built a community for Dataplane optimizations called FDIO, with the idea that we could build a series of services around it, and we've contributed. We have a whole bunch of other sub-projects in FDIO, some of which directly use VPP, other which are kind of related to VPP. A good example of that would be T-Rex, not built on top of VPP, but it's used to test VPP. It's a software packet generator. So we have all these sub-projects in FDIO. So we built a community around VPP, and we call that community FDIO. Well, I don't want to talk too much about FDIO. I want to concentrate on VPP today. So what VPP is a fast and scalable and deterministic L2, L3, and L4 implementation that's being tested. It tested to large scale. It's been tested out to many millions of routes, many millions of concurrent routes, many millions of concurrent flows, to large data throughput. Is also quite deterministic. It uses many of the same optimizations that we pioneered in DPDK. In fact, it uses DPDK for fast I/O. Now, that doesn't mean that it only runs on top of DPDK. It actually uses DPDK as a plugin. So you can turn DPDK off, and you can use VPP without DPDK. And you can use it on top of a Linux raw socket, for instance, an AF-PAC interface. You can use it on top of NetMap, which is an alternative I/O mechanism to DPDK. You can use it on top of various memory interfaces. It actually supports a whole bunch of different ways of actually getting the packets into VPP. But we like to say that it runs fastest on top of DPDK and uses many of the same software optimizations of DPDK. It's based on vector packet technology, which means that it heavily uses both the SSE and AVX instruction sets. So it typically processes 4 packets at a time. So and that loads 4 packets into the cache while processing 4 packets is generally how it works. Same kind of software optimizations as DPDK. And in the same way as DPDK, it's call mode, eliminates context switching, node blocking, and it processes packets in batches. It's extensible, and it really is extensible. So it has a plugin model where you can add your own plugins into DPDK. And one of the key things I just said was that into VPP, DPDK is a plugin. You don't suffer any performance penalty by integrating your feature or your application as a plugin to VPP. We like to say that plugins are equal citizens. There's no performance penalty by implementing your logic as a plugin. It's implemented as a set of directed graph nodes, which means that, and I don't have the deep dive slides here, but you can take it that each graph node is roughly sized to fit into the microprocessor cache, microprocessor instruction cache. So I might load the DPDK input graph node into my instruction cache, and then I pull in 256 packets off the wire into a single vector. And then I will take that single vector, then I will load the Ethernet input graph node into the instruction cache, and I will push those 256 packets into the Ethernet graph node. That means the cost of loading the graph node into the instruction cache is amortized across 256 packets. You pay once for 256 packets, right? It's got other optimizations it uses as well, but you can take it that the VPP pipeline is decomposed into a hierarchy of graph nodes, and it's a directed graph hierarchy in that packets only flow in a single direction. And it's laid out in a logical way that you would expect. You go from your I/O, which is DPDK, into L2, which is your Ethernet input, and then into your L3 layer, which is your IPv4 input. And then IPv4 does a lookup and says, hey, is this local traffic or is this remote traffic? It's remote traffic, I send it back out, I figure out where it needs to go, and I send it back out on the wire. If it's local traffic, I'll send it further up the stack, depending. all the graph nodes are configurable by their own. They may have a control plane interface. They may talk something like IKEv2, or they may talk about something like local link layer discovery protocol. There is a number of control plane protocols that are implemented there, but they also have an API and a CLI. It's a very nice CLI, which I'll hopefully get time to show you in a while. And one of the things I love about VPP is its very deep introspection facilities. You never have a moment with VPP where you say, where the hell did my packet go? It's always very obvious in VPP where your packet went. So you can, and that's not these aren't, how should I say, these aren't debug time features. These aren't features that are only available in the lab to developers. These are features that are actually available in deployed system. The other thing that are also available in deployed system, again, not a developer time feature, is runtime counters and IPC, particularly with instructions per clock. So at any given time, you can log on to VPP and you can figure out where it's really burning cycles, where the bottleneck is in the directed graph. You can also see what errors are being generated. You can see how well it's performing. There's a whole slew of information available at runtime in VPP. I already said it has great packet tracing facilities. And hey, last thing, same as DPDK, it's developed with a standard tool chain. Nothing funky about it. It uses auto tools, make, GDB, GCC. Nothing unexpected. So, I actually have a recent kind of releases slide next, but you can take it as a fully featured layer 2, layer 3, and now layer 4 implementation. And we're going to talk about the layer 4 implementation a little bit more in depth in a while. But at layer 2, you get the kind of things you expect, like MPLS, VLANs, Q&Q, those kind of things. At layer 3, you get the things you'd expect, like IPv4, IPv6, overlay protocols that typically go along with it. One of the things that might be interesting to take us as wireless talk is we recently added GTPU as a feature to VPP. So we have, if you're looking to encapsulate over GTPU, you can now do that in VPP. But hey, there's a whole bunch of actual overlay protocols. One of the big things that we did at Intel this year was we accelerated the IPsec implementation in VPP. So prior to the work that we did in the IPsec implementation in VPP, it was roughly getting about 1 million packets per second through the IPsec implementation because it was based on libcrypto. What we did was we re-engineered the VPP IPsec implementation to use the DPDK CryptoDev implementation. What DPDK CryptoDev does is it takes advantage of the whole platform crypto performance. It provides access to both QAT, which is available in the Lewisburg chipset. QAT is our crypto acceleration unit. Or you can use Encore crypto acceleration, which is the AESNI instruction set. And what we were able to do was we were able to optimize it to the point where with just three cores on the Perley platform, we were getting 100 gigs of IPsec through VPP using the QAT acceleration facility in Lewisburg. Without the QAT acceleration facility in Lewisburg, we were able to get 100 gigs through with 8 cores using the AESNI instruction set on core. In L3, you obviously get things like discovery and get segment routing as well, which is another overlay technology from Cisco. And then in layer 4, UDP has been there for a while, right? So you need UDP for things like VXLAN overlays. Well, then more recently, a TCP implementation has been added, and it's a much talked about TCP implementation. There's a lot of interest in it at the moment. And the TCP implementation is, we'll kind of go into it more depth in a while, but it really is a grounds-up TCP implementation. Oftentimes when you see TCP implementations, it's a reuse of the Linux kernel TCP implementation. I don't know if people are familiar with the Linux kernel as a library project, which is a TCP implementation user space. Another example that uses the Linux kernel in user space as a TCP implementation. Another example would be FStack from Tennyson, which is a user-space TCP implementation based on FreeBSD, and there's quite a few user-space TCP implementations based on FreeBSD. This one's different in that it's written from the grounds up TCP implementation in VPP, which means the TCP implementation itself is not scalar. It's not a packet at a time that you like what you'd usually see in the kernel. It's a vector TCP implementation, which means that you aggregate all your TCP connections in VPP, and then it processes, it processes TCP packets in batches, and then splits them out into connections, and then batch processes connections, and it's very, very efficient TCP implementation. You get quite a mature control plane, so you've obviously got an API, and you've got language bindings for the API to Python, Perl, Java, the kind of languages that you'd expect. But it's also got a very pretty cool CLI, and you'll see that in a while. It's also got IKEv2. One of the things that was recently added in a few, I can't remember if it's the release that's just gone or it's the next release, but we're adding a Bgp implementation in VPP so that instead of, before people were reliant on the Bgp implementation that came with ODL, now actually there's a Bgp implementation actually in VPP itself, so you don't need to rely on ODL to do your route configurations. Usability, it's got language bindings, as I said. It's got plugins for OpenStack and ODL. It's got a plugin directly for the OpenStack Neutron ML2 plugin called Networking VPP, and it's also got support for ODL for group policy-based routing. It's also got support in Kubernetes and Flannel. Sorry, not Flannel. I think that's actually incorrect. It's actually Contiv now. So a lot of work has been done stitching VPP into Contiv and Contiv as a CNI provider into Kubernetes. And now we're drifting into the control plane stuff where I feel very, very unsure. So I'm going to move on. And then finally, we've got OSV packaging, which means that hey, if you're using Ubuntu or Debian, we've got you covered. If you're using CentOS or Fedora, we have packaging for you as well. So then, look, I'm not going to talk through this slide in depth, except to say that the VPP as a community is being rapidly evolving. You can see there's a whole slew of features that have been added in 2017. One thing that I like to talk about here, I like to talk about two things here. One thing that I like to talk about is obviously that we're adding a mass of features over time. The other thing is that we're doing a lot of work, performance testing, to make sure that as we add features, we're not actually degrading performance as we go. And this is a key thing, and it's a key tenet of FDIO and VPP, in that we have a sub-project called CSIT where we're constantly measuring. We run performance tests on VPP for a large set of test cases to make sure that as commits get added to VPP, there's no degradation in performance. So as it becomes more featureful, as may be the case that's experienced perhaps with other projects, as typically happens is as a project becomes more featureful, you usually pay a cost in performance. We're pretty determined that won't happen in VPP, and we have a whole series of test cases in a sub-project called CSIT that are tested continuously to make sure that as we get more featureful, we're not dropping performance. One of the common themes, you can see a couple of common themes in, let's say, 2017. One was IPsec, which I just talked about a few moments ago. Another one has been the TCP implementation. There's a lot of work. The initial version of the TCP host stack was made available in 1704. And then a lot of RFC compliance testing was completed between 1704 and 1707. So it became a much more RFC compliant TCP implementation over that period. Something again that was added in 1707 was a series of interfaces to support containers. So to support VNFs and containers. One was MEMIF and the other one was Virtual User. And then there's been a whole bunch of networking features added since then. Another thing we added was GRE over IPv6, which was another overlay. That was something that we added. But look, I'm not going to read through this at length. I just really wanted to leave the two impressions. We're adding features. List is growing with every successive release. but also performance is not being compromised as we add more features. Okay. Now.
Quick question on the TCP stuff. You mentioned there are multiple, if there are multiple TCP sessions, connections, then you can batch it, etc. You'll definitely get a much more better performance.
Yeah.
A single TCP connection, the Linux kernel stack has tons of pretty interesting TCP modifications. Like initial window can be higher, window scaling, adaptive stuff. There's so many things actually. But given this stack, probably will be very much, as I looked at it, it says fast recovery and basic TCP state machine, right? So probably it doesn't apply for the single connection case, that's my understanding. Or if you add those kind of features which Linux already has, then maybe it might be comparable. That's part of my observation.
So when you aggregate all of the TCP processing in the vSwitch, you can make a lot of the economies of scale that we talked about, the kind of optimizations that we talked about, the TCP implementation gets the benefit of. So if we think about if you think about what the kernel does, the kernel, and by the way, I've worked in and out of the Linux kernel for years, but I'm a huge fan of the Linux kernel. What it does, like one of the things that it implements is GRO. So that's the ability to assemble the TCP stream in the networking driver before it pushes it up the stack. Why does it do that?
The segmentation offload you're talking about.
It does that to assemble basically a jumbo frame. And so you're not paying the per packet cost. The per packet cost as you move the packet up the stack. Whereas what we do is we flip the stack on its head. So it's not those kind of costs that are typically associated with GRO turned off, where you're paying for a function call for every action you do on the packet. So GRO's way of solving that is to aggregate all the packets together and to process them all at once. Well, we do 256 packets at a time, typically in VPP. So it's similar in that respect. But then we also get the benefit in the TCP implementation of things like the vector instructions, things that the kernel typically doesn't use. So the TCP implementation that we end up with, actually implemented in VPP, uses microprocessor optimizations that typically aren't used in the kernel. And also it gets the benefit of those kind of optimizations we talked about before, like the amortizing the single instruction cache load across 256 packets. The kernel does part of that by GRO, but I'd argue that we actually end up with a more efficient.
Yeah. Another thing is a branch prediction, like if likely, unlikely kind of instructions in the kernel. Just before, one last question.
Well, there's another way of approaching that, and that's again the way the TCP. So when you say likely or unlikely, what you're doing is you're giving hints to the branch. You're giving hints to the branch prediction unit. Whereas one of the fun things, one of the interesting things that VPP does is it assumes that all of the packets are going to the next default graph node. It assumes that all packets are going to the next default graph node. And then it goes back and it handles exceptions on a case-by-case basis and then changes them. And it actually turns out that's actually far more efficient to do, to make assumptions that, hey, I've got 256 vectors. And a good example would be, let's say, IPv4 lookup. You make the assumption that they're all going to get looked up and going to go out on the wire. But then you go back and you identify the ones that are actually local packets, because out of the 256 packets, they'll probably be just onesie twosies out of 256 packets, and you identify those on a one-by-one, and you handle those on a one-by-one basis, and that's far more efficient way to use the branch prediction unit.
Yeah, one last question on that. Your last slide mentioned about tracing mechanisms. So,
yes.
What kind of tracing mechanisms with zero overhead you're using?
I'll show you in a while.
Hi, 2 questions.
Sure.
You mentioned BGP. It's a Dataplane processing. All you need to do is to look into its me destination 179, potentially if source is configured, and punt it to the application. What do you do specially for BGP?
I'm sorry, I didn't quite catch the
You
question.
mentioned BGP
Yes.
specifically. It made sense when it was an ODL at the management layer.
Yes.
What are you doing now specifically?
So that I don't actually have the detail of. So all I know at this point is that the BGP implementation was previously handled by ODL. No, I know one thing that we're trying to do is decouple VPP. So one of the things, for instance, we can have the networking VPP plugin. So you have an ML2 plugin directly from OpenStack down to VPP with no dependency on ODL. And then for those people who are using the ML2 plugin, not using ODL, I think the BGP implementation was made available in VPP for those set of users who weren't using ODL. But that's as much as I know about it.
Second question, gRPC. So streaming telemetry, I remember
If you do send me an email about it, I can find out more information.
gRPC. Intel last year announced that gRPC is going to be implemented very low layer, somewhere within SPDK. And are you going to use gRPC for telemetry streaming?
I don't, gRPC, general.
Google RPC?
Hmm?
Google RPC.
Oh, Google RPC. Oh, that's a good question. So no, I don't know where, okay, so there's Golang bindings for both, I know of a project that's doing Golang bindings for both DPDK and another project that's doing, there's a new sub-project in FDIO. I know neither of these are gRPC, right? For FDIO, but I don't know anybody who's doing gRPC for either of them. So this is basically like what VPP has is VPP has pretty much a binary socket implementation. So it has a way to talk to it over either TCP sockets or Unix sockets, but it's not quite an RPC. I wouldn't quite call it an RPC implementation.
It uses netconf push nurse bound
Okay,
today,
well-
which is very inefficient.
Well, okay, to be precise, what it does is you talk netconf and yang to honeycomb, which is, and then honeycomb talks to binary API to VPP. But I'm not aware, I know there's Python language bindings, and I know there's Java language bindings. I'm not aware of any gRPC implementation. Okay, so how am I doing for time?
You are at your 15 minutes.
Oh, okay, gosh. All right. So you end up with two problems. One is how do you talk from a VPP-based vSwitch to containers? And how do I run VPP and DPDK inside containers? How do I talk from a DPDK or VPP-based vSwitch to containers? Because remember, VPP and DPDK are user space and containers are really an entity at the kernel. And then also, how do I run DPDK and VPP efficiently inside containers? So those are the two use cases I'm going to talk about. So the first use case is, how do I efficiently run DPDK and VPP in the kernel? So how do we efficiently run DPDK and VPP in containers? So you might remember the matrix, the list of characteristics of containers and microservices I presented earlier. Well, I like the picture of the round peg in the square hole because I think that kind of roughly describes where our starting point was. We weren't container friendly starting out. And whereas I think the kind of microservices, how do we get to a strict microservices model is still some way off. I think there's a lot we can do today and a lot we are doing today to make ourselves more container friendly. One of the things that we're doing is that we're optimizing the startup. So we're getting DPDK to start up faster. You can do things like if you know you're running inside a container, there's no need to scan the PCI bus. There's no need to look for contiguous memory if you're using a pure virtual memory interface. You can do things like you can use 4K pages instead of using huge pages, and you can use late binding of huge pages. You can also, we already support interrupts in order to do better core sharing. So we also have an interrupt-driven model in DPDK instead of a poll mode model in order to share the cores in a more efficient way. And then we also have enabled multiple I/O methodologies for containers. So you can support SRI via pass-through, that's taking a virtual function, passing it through to a container, and then running DPDK on top. But we also have a virtIO user, which is a pure memory interface from your virtual switch into the container with DPDK sitting on top. Similar story in VPP, which is that it actually starts up relatively quickly if you're not using DPDK as a plugin, if you're running on top of a raw socket. Obviously, we want to improve the situation where you are using DPDK as a plugin. You can use the VPP's own memory model, which already supports 4K pages and late binding. And then VPP, same as DPDK, already supports interrupt mode instead of whole mode, SRIOV in containers, and instead of, in addition to supporting virtual user, I should say, it also supports its own memory interface into the container called memif. So all of these are activities that are in flight at the moment that you'll see in DPDK. Oh, this is a good one. I think 1708 is live, so I think it's 1711 is where you'll see a lot of this will see the light of day. Pretty much, but the two key takeaways that you can take away are that we are making the key takeaways that you can take away is we're making DPDK and VPP more efficient in terms of how it shares cores. We're making it more efficient in terms of how it shares memory, and then we're also making it start up and shut down faster for more friendlier container deployments. Okay, so that covers deploying a DPDK or VPP inside a container. What if you're a DPDK or VPP based vSwitch? Or this is where you use DPDK or VPP in your NFVI and you want to talk to containers. Because many of us, many deployments already use DPDK and VPP as their vSwitch for talking to their VMs. Now we want a situation whereby we're using that same technology to talk to containers. So this is where the TCP implementation becomes interesting. So VPP already supports memif for VNFs. So if I have a VNF in a container, I can talk to my virtual switch over the VNF interface. So that's a pure in-memory interface where I share a memory I/O area between the virtual switch and the VNF, and then I punt my packets over it between my VNF and my virtual switch. And you can do that already today with both DPDK and VPP using either virtual user interface or using memif. It's already well supported. So this is really where you have a VNF. The VNF expects a raw packet interface, not too dissimilar to VPP. It's not too similar to DPDK. That's already well supported for those kind of container deployments. But that's where you see all of the kind of characteristics we talked about before coming into play for the VNF in the container, ability to start up and shut down faster, etc. From the vSwitch's point of view, the vSwitch sees a memif interface or a virtio interface, not too dissimilar to the virtio interface that it's been using already for VMs. Where it gets different is when you want to start talking to socket applications using this methodology. And this is, remember, this is all bare metal deployments now. This is containers talking to a vSwitch in the default namespace. So you might have a socket-based application in your containers. Now, the model that's been supported up until this point has required that you hairpin the package through the kernel in order to get up into the virtual switch. And it's very commonly done at the moment, which is that if I have a socket-based application, that socket-based application expects to talk to the kernel. The bit stream, the TCP bit stream flows from the socket-based application in the container into the kernel, then goes into a vETH, and then from the vETH front end in the container to the vETH back end in the default namespace, and then hairpins back up into the vSwitch. So I think you probably can count 2 or 3 context switches along the way there, 2 or 3 memory copies along the way there. Doesn't really sound terribly efficient. So what the work has been happening in the VPP community has been to develop what's called the Ld Preload Layer, which will intercept the socket, the TCP bit stream, as it leaves the socket application. So the socket application doesn't really know anything has changed. The socket application still thinks it's talking to the kernel. But that bit stream, that TCP bit stream, has been intercepted by the Ld Preload Layer and now is redirected over a shared memory interface not too dissimilar to memif into a TCP implementation in the vSwitch. So this is where the scaling really starts to happen. So you no longer have a real interface. It's a lightweight in-memory interface compared to a vETH. The socket-based application doesn't know that anything has changed. The socket-based application still thinks it's talking to the kernel, but now it's talking to the aggregated TCP implementation in VPP, and that aggregated TCP implementation is designed to scale to many thousands of containers. because you don't have a real kernel interface, because it is a relatively lightweight interface in the kernel, and because because you're implementing a vector TCP implementation in your vSwitch, you're ending up with a far more scalable TCP implementation that should support many more thousands of containers. So this is one model. This is a model whereby I want to use, this is one model, there's a lot to like about it. And this is where I want to support a bare metal deployment. And where I have a memory interface between my virtual network function and VPP, and then I use the Ld Preload Layer between the container and VPP. Now the Ld Preload Layer is in development at the moment. You can imagine that out of the box it will support Nginx, Node.js, Redis, but it won't support every socket-based application that exists. So we also need a transitory approach, a way to transition for those set of applications, that may not be supported by the Ld Preload Layer over time. And because of that, we're supporting another model, which is called the master VM approach. And in this approach, you deploy all of your containers in a single VM, the master VM. And the benefit that this gives you is that you can continue to use the Linux kernel in the way that you've used before, that you've used it for virtualization. You get the benefits of VTX in that VTX deprivileges the Linux kernel, and by deprivileging the Linux kernel, deprivileges the container as well. So your socket-based application running inside the kernel, your socket-based application running inside the container talks to the kernel. The kernel is now running in user space. It's running up in ring 3 by virtue of VTX, by virtue of virtualization technology. And then it talks to the virtual switch over a plain old VirtIO net connection that we've been using in virtualization for years at this point, 7 or 8 years at this point. This is already a very well supported model. We have VirtIO net drivers in DPDK for the last 5 or 6 years. And VirtIO net has been supported by the Linux kernel for the last 5 or 6 years. What we're doing here is we're using the benefit of virtualization technology, VTX, to deprivilege the kernel, and by deprivilege the container, and by moving the container up into user space, we can use the standard virtualization toolchain to talk to the container. So I can talk to it over VirtIO net, an interface that's already well supported by all virtual switches. I can use vhost in order to set up the shared memory blob between either the virtual switch and DPDK running inside the container, or between the virtual switch and the kernel, the kernel's interface inside the container. So what this does is has a leveling effect. I can now talk to my container in the same way I talk to my VM. I don't need to make any special adjustments. And in this way, this is why I talked about it being a good transitory approach along the way to containerization and microservices. Because for many people will be in a situation whereby they'll want to run all of this concurrently. There won't be a big bang in their network where they'll turn off their virtual machines one day and turn on all of their containers another day. That's just not going to happen, right? We can expect that virtual machines will have a long tail into the future. They're going to be around a long time. So we are going to need NFVI that will support both virtual machines and containers concurrently. What this does, or what this approach, the master VM approach does, is it makes it transparent. Your containers look like your virtual machines as far as the vSwitch is concerned, and your containers look like your virtual machines as far as your NFVI, as far as a lot of your NFVI is concerned. So it has this leveling effect. So I might have a DPDK deployed inside a virtual machine, and I can talk to a DPDK-based vSwitch over a VirtIO net connection. Or I might have a socket application deployed inside a virtual machine. I could talk to my DPDK-based vSwitch over a VirtIO net connection. Or I might have a DPDK VNF or a socket-based application talk to a container deployed in a container within the virtual machine. And it talks over the exact same VirtIO net connection. Now, some people, when they've seen the slide, they come to me and they say, well, you know, Ray, you don't get the point. Containerization is the rejection of virtualization. I was saying, well, I don't want everybody to run lots of virtual machines. I just want you to run one virtual machine and put all your containers in it. Because that lets us use VTX to deprivilege the virtual machine, and then I can use the same virtualization toolchain to talk to all those containers. I still get the economies of scale, and I still get the efficiency of containers, but then I also get the benefit of VTX to deprivilege the containers, and I've got a much nicer way to talk to them from my NFVI. Okay, so how am I doing for time? Okay, I've got a question here.
So you had mentioned about the Ld Preload.
Sure.
So I can understand that it is essentially going to handhold the packet from the container space onto the vSwitch.
Yep.
So, but can you throw some light on what context this is going to run? Is it just going to be as simple as a function call or an API?
So the application itself, so if you think about how an application, a Linux application typically runs, you run your application and it calls the runtime linker. And the runtime linker says, I need to load glibc and I need to load these other libraries. So what they use is they use a facility in the runtime linker called Ld Preload that loads a given library before everything else. So that POSIX API call that we're all familiar with, the listen, the connect, the send, the receive, and then the read and write, and all of those other semantics, all of those API semantics you expect with a TCP implementation, they no longer are calls to glibc. The application still thinks they're calls to glibc. It doesn't know anything's changed. But now they're actually called to this Intercept library. So the Intercept library, now is responsible for handling the TCP connection. So an example might be the Intercept library might get a listen call, and then it sets a flag inside the VPP vSwitch to say, hey, if you see any packets that arrive at this IP address and this port, send them to me. Send them over this shared memory area to me. Similarly, when packets are sent and received, when the VPP has a session implementation, has a notion of a TCP session, it's going through the TCP sessions. It will see that socket, it'll see that port number, and it'll see that IP address and say, okay, that's belonged to this bit stream. I'm going to push it in. I'm going to put it into this. I'm going to put it into the TCP window for that bit stream, and then I'm going to wake up that socket-based application in the container way to process the bit stream. So all of the API calls that you'd expect to go to the kernel are now faked out by VPP. The socket doesn't know anything has changed. It still makes a select on the socket to be woken up whenever the TCP bit stream has become active. It still does a listen for new connections. It still does all of the things that it's done before. It shouldn't know anything has changed. But what it does end up in the case is you are aggregating all your TCP processing in the vSwitching and getting those economies of scale. And then you're also removing the VEATs from the equation. So you're ending up with a much lighter interface into the application. But theoretically, the application wants to scale. Now, anybody who's done any socket-based programming will be able to tell you that the different permutations of different options you can select on sockets, there's a very, very, very large number of permutations. It's actually all different permutations. I can do forks, and what happens to my file descriptor when I fork. There's also what happens, there's a million different ways to use the TCP API. So that's why my expectation is that we're going to need both approaches for a while. So my expectation is that there'll be a couple of high priority applications that we all know and love in this room, like the Nginx's of this world, and they'll be made to work great against this Ld Preload layer. But for all those many different permutations of TCP applications, we also have the second approach, which is to use the existing kernel stack and to make containers more friendly to the NFVI by using virtualization to deprivilege. And I think it'll be a mix of both. It will come to a mix of both. Well, it may be the case, and I hope it will be the case, that we'll scale the first approach to support all socket-based applications over time. But we're going to need multiple tools in our toolbox in order to support a scalable container data plan. Sorry, I have a question there.
So, thing is about select and epoll is more tricky. Because
I'm sorry?
Select and epoll, for example. An application.
Selecting a...
And selecting and epoll.
Yeah,
Two system calls.
They're the two trickiest ones.
Because the application can open, let's say, FD for a Unix domain socket.
And they're the hardest ones to get to scale. So what's actually interesting that's happening is not only is there the Ld Preload Layer is being made available, but a native TCP implementation, a native library to talk to the VPP TCP implementation is also in development. Because as you quite rightly pointed out, that the two hardest API calls to get to scale are epoll and select. They're probably the two most inefficient. So if you are willing to put the investment in to rewrite your application to talk directly to VPP, there is a second library that doesn't use doesn't use epoll or doesn't use select, but pretty much implements all of the other BSD SOCKS API calls. By the way, that's a common theme you see in all the TCP implementations is they all end up with epoll and select as a bottleneck. So the second library is not transparently loaded by application. You have to consciously link against it and use its API, but you end up even more scalable again by virtue of not having to fake out epoll and select. So that was a great question.
I have a question.
You mentioned you can connect VPP with the containers with either MEMIF or the
Yes.
socket over what's that, Ld Preload.
Yes.
Are those interfaces still wrapped by standard network stacks, or you can pass some private data along with your package over those kind of?
So those are very much raw interfaces. They're kind of like.
Can you repeat the question?
Oh, sorry. Oh, right. So do the apologies. So the MEMIF and VirtIO, the MEMIF and VirtIO user interfaces, do they pass to the entire network stack? They do. So when you receive packets via the VirtIO net connection, it depends on which network stack you mean. If you mean the VPP network stack,
Right.
the answer is yes. Do they pump packets into the kernel? No, not unless you do something extra. But yeah, as far as VPP is concerned, I remember at the head of the presentation I said VPP supports lots of I/O methodologies. This is another I/O methodology that VPP supports.
But can you pass private data along with the packet over those kind of interfaces?
It actually came up. That came up recently in the mailing list. Was that you in the mailing? Because that question came up in the mailing list recently, and the answer I can't remember off the top of my head. If you send me an email, I can chase it.
Okay, one more question.
Yeah. Pretty much you are doing what the kernel has been doing for quite some time. One of the reasons why we have this isolation or the separation between the kernel and the user space is that user space would not be able to corrupt the kernel. Now, if you're pushing all this processing into the user space, anybody can step onto anybody else, especially if you have shared memory. Even multiple containers can step on each other. And how are you going to address that? And it also adds to the security issue.
So that's a great question, and I've heard that a number of times. And and I can dial us back all the way back to the operating system designs in the 70s. So, you ended up with the executive. And the executive took care of device management. Took care of things like managing the time in the CPU, managing I/O, and managing memory. But it was a very different model. In that model, the networking wasn't the application. When we're implementing a VNF, for instance, networking is the application. So it makes sense in that case to have a user space, when the networking is the application, it makes sense to always run the application user space. So that, hey, I'm protected by an IOMMU. So if I have an errant DMA, I don't bring down the whole system. I only bring down my application because it's in user space, hey, I can spin it up again. Whereas, my argument very much is once the networking becomes the application, as it is in DPDK, as it is in VPP. The same with any other application that runs on top of the system. It makes sense to run in the user space.
VPP and DPDK, they are stateless. For example, one packet has got nothing to do with the other packet. Whereas if you bring down the sockets, that brings down the application itself, pretty much.
That's true, but you can make the argument there it's no more or less failure resilient or resistant than the kernel, because if you're aggregating all of the TCP processing in the kernel, the only delta is at that point if you have an error and you bring down the entire system. Whereas if you have an error in DPDK or VPP, you only bring down the virtual switch, and you still have the opportunity to spin it back up again. Okay, I'm done. I'm yanked off. Do I honestly have no time for a demo? Okay, it doesn't.
Dr. Sujat.
I need 2 minutes.
Yeah.
Okay. So I'm going to do something really simple. I'm going to create a couple of. I have a couple of containers that are spun up. One's called container 1, one's called container 2. They have a V8 backend, which is called V8C1, and it has V8 backend, which is called V8C2. I'm going to put them up out of the default namespace. I'm going to pass them into VPP as a vSwitch. And how I do that is I tell VPP they exist. I say create host interface name V8C1 and C2, and that creates interfaces in VPP for the V8s that talk to C1 and C2. I'm going to set their state to up because I want to talk to them, and then I'm going to set them into a bridge. I'm going to add them into an L2 bridge. So this is nothing terribly fancy, and then I'm going to show you that they're added into the L2 bridge. And then because I'm doing all this with my neck kind of crank, I'm going to just copy and paste if that's okay. Okay, so sudo VPP control, so this gives me access to the VPP CLI. A lot of the facilities that we talked about there's runtime statistics, there's errors, things like that. Okay, so now I'm going to show you the interfaces beforehand, show int. Okay, I've only got the localhost interface, the loopback interface. So I'm going to pick up my, okay, where's my, okay, it's over here. So, okay, so now what I've done is I've created my, my virtual interface, 2 virtual interfaces in VPP, one to talk to C1, one to talk to C2. I've added them, I've set them up, and then I've added them to my L2 bridge. And I'm going to show you my L2 bridge now. Okay, there's my 2 interfaces, and they're both added to VPP's L2 bridge. So then I'm going to do something, I'm going to jump into container 1, C1. So now we're in C1. Okay. Where's Notepad gone? There it is. So now I'm just going to add an IP address in C1, so you can see me just add an IP address to the V8 in C1. Okay, I've added an IP address to the V8 in C1. And then, predictably, I'm going to add an IP address to the V8 in C2. Where's my mouse pointer? Oh, it's over here. Whoops. Yeah. I've just made a huge mistake. So of course, this is usually why demos blow up, but we'll try. Okay. So now I'm going to flip over to C2, SSH C2. And I'm going to add the IP. Okay, so now I'm going to ping 172.16.13.12. And there we're pinging. And you say, okay, well, that's not miraculous, right? You likely are pinging not through the virtual switch, but through the Linux kernel. So like any good magician, I'm going to show you that I am actually pinging through the virtual switch. So I'm going to add a tracer to the graph node, the AF packet graph node, which picks the packets out of the Linux kernel and pulls them into VPP. So I say, okay, trace, add AF packets. So I add a tracer to the AF packet graph node, which pulls the packets out of the Linux kernel and pushes them through VPP. So I have a trace, and then show trace. And there we go. So by way of an example, there's packet 6 that got pulled in. It arrived on the AF packet graph node. It then went into the Ethernet input graph node, who said, is this packet for me or is this for somebody else? This packet's for somebody else, and then it pushed it into the bridge. And then in the bridge, it decided where it needed to go, and then it sent it out on the host V8C2 output. So it sent it out to the right container. Oh, sorry. Incidentally, that was the reply. That was the reply, not the echo request. So that was it. As simple as could be. I had two containers, C1, C2. I had VPP acting as a vSwitch between the containers. I redirected the vEats back ends of the containers out of the kernel and into a VPP vSwitch, and then I pinged packets through the vSwitch with just a handful of commands. Simple as can be. Okay. I think I'm well out of time at this point. I am well out of time. Thank you so much.